Well, then we can chat about vectors today. Today we're starting section 8.3. Section 8.3 has got a lot of stuff in it, so we'll spend quite a while playing with it. But it is talking about vectors. Depending on your background, you may have worked a little bit with vectors before, or even a lot, or you might not have seen them almost at all. But vectors are a very important idea in mathematics and physics and certainly in the hard sciences, but also in the softer sciences. Vectors are used a lot in finance, in anytime you're modeling different things, we'll use vectors quite often. So I want to start off very kind of basic with it, with just kind of what is a vector. So I want to start with that question. What is a vector? So a vector is a mathematical quantity. It is considered a quantity, but it is a mathematical quantity with two qualities to it, with both magnitude and direction. We're going to spend a little while talking about what that means. So magnitude gives us an idea of amount. So you can think of this magnitude as how much. Could be how much, could be how far, could be how valuable, could be, what proportion, some sense of value. So this, in terms of magnitude, it acts a lot like a normal, kind of like a normal number does. So it's got some kind of numerical value that can go up or down, that can increase, decrease. It's got some number to it. It's also got a direction. Now, this direction can be a spatial direction, so it can be up, down, left, right, kind of an idea of orientation in space. But it doesn't necessarily have to be that physical. It could be something as kind of abstract as increase versus decrease. Like, for example, if you've got I'm going to go with politics. If you've got a ballot measure that is becoming, that more and more people are liking, you might have your, support for your ballot measure went up by 5%. That is describing a vector because it's describing an amount, in this case, an amount of change, 5%. So it's got a magnitude, but also it does have a direction associated with it, an increase in magnitude, a growth. Now, a lot of times we will think of these more in terms of, spatial directions, left, right, up, down, or going at a particular angle or whatnot. But keep in mind that these things are often more abstract when we're not talking about physics applications. We often depict vectors as what's referred to as a directed line segment. So, or put more simply, an arrow. That arrow has an initial point where it starts, and the end with the arrow on it is often referred to as a terminal point. Similar to the initial point, initial side and terminal side that we're used to for angles. You often see that initial point referred to as the tail and the terminal point as the head of a vector. Kind of like you would a snake. Snake's got a tail end and a head end. We use arrows or directed line segments to represent vectors often because they have two aspects to them. They have a magnitude depicted by how long the vector is. So if we want it to be longer, draw a longer arrow, smaller magnitude, smaller arrow. And we can associate with it a direction by the angle it's put at. So in terms of some reference, we can associate that with an angle. I've referenced it here to the vertical, but it could be referenced to anything. As long as that reference is fixed for your entire problem, then all your vectors have an associated direction to them. So it could be measured that way, or it could be measured horizontally. It could be measured from any orientation. Now, this is a two-dimensional vector because it's sitting in a two-dimensional space, but you can also imagine that we could have a three-dimensional vector, something that's coming out away from a three-dimensional location. So actually, I want to use the other tool for that. See if that works better. Give it some thickness. That doesn't matter. So that's it. Try to make it look a little more three-dimensional, but yeah. So coming out in free space, it still has a magnitude because it's got a length. It's still got a direction. That direction is going to have to be described more than just by one angle. We can describe that vector in a couple different ways, but we can have three-dimensional vectors. We can even have four-dimensional vectors, five-dimensional vectors, any dimensional vectors that we want. In terms of kind of our normal numbers, we often think of our normal numbers as being on a number line. We've got 0, 1, 2, 3, 4, 5, 6. So if we want to think of that number 2 as just a value, a location, that number 2 all by itself is what we refer to as a scalar value. It's got a magnitude but no direction. So most of the numbers, or what we generally think of as our numbers, we'll call scalars, magnitude without direction, but we could assign that to a direction and say it is 2 in the positive. Well, now it has both a magnitude and a vector, or sorry, both a magnitude and a direction. So we can start thinking of our numbers both as scalars or as vectors, depending on what we're doing with them. Eventually, you get far enough in mathematics and physics, and you start considering just about anything to be a vector, as long as you can assign it both magnitude and direction. We will probably stay mostly in the field of our vectors being either um, motion, so they'll be talking about velocity vectors, position vectors that just tell us location, and force vectors. So that's probably the three most common vectors that we'll use in this class, certainly, and three of the most common ones that you see in physics. You also get things like acceleration vectors and momentum. You get all kinds of vectors in physics. But these are probably the three kind of nice examples that we're work with in this course. So if we want to imagine we've got a couple of vectors here, let's say they're both representing force, and we've got this first vector, I'm going to call this vector V, just to be creative. When we label something as a vector, we want to show our audience that it's a vector. And we generally do that by putting an arrow above it. So you'll see vectors depicted with a little arrow on top of them to say that that V, by the way, is a vector. Now, a lot of textbooks don't do this. Instead, they'll write their vectors as bold. So you'll see a bold U or a bold V or a bold whatever to represent vectors. That's a kind of an old-fashioned tool from when it was hard to type things like arrows above letters. Nowadays, with the modern computers, you just put a little shortcut key on your keyboard and you can type all the little arrows you want over things. But old school, it was a little bit harder to get to where you could type it. And really, modern textbooks should just go back to putting the arrow above things, but a lot of them don't, mostly because they're lazy, I think. But if we've got a vector V, say it's, V is 10 pounds of force. 10 pounds would be its magnitude in the indicated direction. The indicated direction. So 10 pounds of force in that direction measured from some reference point. We can have another vector, I'm going to call that vector U, also force, so also going to be in pounds, and it's headed in a different direction. It's a little shorter, so U's magnitude. Now, I don't want to have to say, like 7 pounds of force in the indicated direction. I just want to be able to tell you what its magnitude is. Now, I could say the magnitude of U is, say, 7 pounds. But even that's going to be kind of annoying to have to write out over and over again. So I do want some symbology for the magnitude of. And the nice thing is we have a notation for it. It looks kind of like absolute value, but there are 2 bars instead of 1. And it means something very similar to absolute value. Absolute value is like how big is the number, don't care if it's negative or positive. Magnitude is the same thing, kind of takes away the direction and just leaves you the vector's magnitude. So the magnitude of U is 7 pounds of force. The magnitude of V up here is 10 pounds. I don't have to put the pounds on it, but I'm gonna just to keep us straight. Now, it would seem reasonable that if we took vector V and added vector U together, well, this is 10 pounds of force and that's 7 pounds of force. So if we add them together, shouldn't we get 17 pounds of force? But unfortunately, or fortunately for the world existing the way it does, we don't get 17 pounds of force. Because these vectors are pointed in different directions, the sum of the two vectors is not simply the sum of their magnitudes. They're going different directions, so they're reinforcing each other somewhat, but they're also fighting each other a little bit. This vector is trying to pull upward some, while this vector is pushing downward some, and those upward and downward forces are going to want to cancel each other out. So if we want to figure out what this resultant force is, not only in magnitude but in direction as well, we've got to come up with a tool for adding vectors together. And there are two of them. There's, if we want to go really old school, what we would do is draw them. You'd get a very accurate measurement of both the angle and the direction and draw one of them. If these two vectors have the same length and are in the same direction, they are the same vector. Vectors don't have position on them. We can move them around all we want. So those vectors, if I've drawn them with the exact same length and angle, they are the same vector. So if we move one of the vectors to put it down here, haven't changed the vector. Still going in the same direction, still the same length, same vector. So old school, what you'd do is you'd really accurately depict that length and that direction. And then you'd do the same thing with that vector u, except that you'd move it so that its tail is on the first vector's head. It's called head to tail method for adding. And you would very accurately copy the magnitude and direction of that other vector. So these two vectors, these two forces are acting on, let's say, the same object here. What's the result of those two vectors? Well, that result is going to be the vector that connects the head and tail, or the tail of the first to the head of the second. This result is our vector v plus u. Notice its length is not as long as the sum of the two. If that, again, the length of v was 10, the length of u was 7, that length of u plus v is not the full 17. It's less than the 17 because the vectors were not headed in the same direction. And again, old school, if we want to know how much force there was there, we would measure this as accurately as possible. And let's say, for sake of argument, that magnitude of v plus u, if we measure it super carefully, let's say it's 15, then we would know our resultant force on this object is a resultant force of 15 pounds in this direction. So what direction is this object going to move in? Well, the object is going to be pulled in this direction, a little shallower than v, but upward from where u is, with a combined force of 15 pounds. So 15 pounds going in that direction. Now, for a long time, and I mean like hundreds, thousands of years, you did your force diagrams or your position diagrams, if you're doing architecture or any of that kind of stuff, you did your vector mechanics this way, very geometrically. You drew them out extremely accurately. You used compass and straight edge techniques to carefully copy over vectors. If you've ever seen like an old sailing movie or an old pirate movie. They had the map on it with all those tools, all the compasses and straight edges and weird rulers that kind of stacked over. A lot of those tools were for carefully copying over velocity vectors and position vectors to figure out where you were. If you had gone in a particular direction for, at say, a particular speed, if you had gone this direction, say 70 degrees, 70 degrees east of north at, say, I don't know, 50 knots. So your magnitude is the 50 knots, your heading is your direction, but the current was going this way at, I don't know, 25 knots, and you wanted to figure out where you ended up. Well, if you knew the direction of the current and the direction of your ship, you could draw out where you expected yourself to be and figure out, well, how long is it going to take me and where am I going to end up based on that information. Had the advantage of being geometric, so all of the geometric tools worked nice. Had the disadvantage of it was only as accurate as your measurements and your drawings are. But we still use vector diagrams like this today for many, many, many things. Any of you going into physics, you will really enjoy all the vector diagrams you get to draw. Because they're still very helpful for us in setting up and understanding how things like forces and speeds and accelerations and gravities and all those kind of things, all those things interact. But we certainly want kind of a better way to work with vectors where we don't have to be reliant on our drawing ability. So what we want to do is kind of build up a rigid way or a more computational way of dealing with vectors. And that method, instead of dealing with our directed line segments or our arrows, directed line segments is the formal term, but instead of dealing with our directed line segment vectors, we're going to start looking at vectors in component form. Now, what do I mean by component form? Well, we're going to build a couple of building blocks, mathematically well-defined building blocks. They're actually formally referred to as a bases that we're going to build all our vectors from. And the nice thing about these building blocks is they should be fairly familiar and usually fairly reasonable for most people. Now, as I said, this is formally referred to as a bases. This is referred to as the standard bases, the one we're going to use. There are other bases, and you can get into a whole bunch of cool vector stuff when you take linear algebra. That'll be next spring for those of you who do calc and your main maths sequence next year. So you have a linear algebra is essentially a course on vectors. But you'll get into that later. So the two building blocks that we want to use, we want them to be as simple and kind of almost generic as possible. We want kind of fundamental building blocks for everything. So those two building blocks we're going to use are a vector of magnitude 1. So that length is 1, headed in our x direction. So we're going to put our vectors into coordinate systems because coordinate systems are very nice and useful. And we're going to make a little magnitude 1 vector in the x direction. And that's going to be our first building block. That building block is a vector. It does have a magnitude of 1. It is pointing in a direction, the positive horizontal. So it is a full vector. And we're going to give that vector a name. And that name is I. Now notice I didn't put a dot yet. Since it's a vector, instead of putting the dot, we would be tempted to put an arrow on top of it because it is the vector I, but we don't. Instead, what we put on it is, is a little hat. Now that might sound silly, because it is, but that really is read as I hat. I hat. The hat in vector notation, the hat refers to of magnitude 1, or a unit vector, meaning a vector of 1 unit magnitude. We'll talk more about unit vectors in probably a day or so, but that little hat does indicate that this is a length 1, a unit vector. It's a fundamental length vector. So that's our first building block, 1 unit in the x direction. Our second building block will probably not come as a surprise. It is a length 1 vector in the vertical. And these two vectors will form our building blocks that we'll be able to build any other vector out of. We call this vector the horizontal vector I. Any guesses what we call the vertical vector? Be nice, wouldn't it, if it was J? Well, you're in luck, it's J. But again, J hat. So I hat and J hat, little length 1 vectors, and using those, we'll be able to build any other vector. How are we going to do that? So let's say we've got some vector out here. We plant that vector in a coordinate system. Doesn't have to come out from the origin. It can technically be anywhere in that coordinate system. Vectors are sometimes referred to as position invariant. Doesn't matter where they are, they're the same vector. We talked about that a little while ago. But if we want to depict this vector in terms of our bases here, in terms of our building blocks, we're going to take that vector and look at, well, how many little length 1 I hats does it take to make that vector versus how many j hats does it take? It's almost like a slope argument, kind of a change in x, change in y kind of argument. So to build that purple vector v, it took how many i's? It took 1, 2, 3, 4, 5 i's. So 5 I hats plus how many j's? 1, 2, 3, 4. So 4 j hats. That's what it took to build our vector v. So we can express that vector v in component form. 5 i's plus 4 j's, 5 I hat plus 4 j hat makes that vector v. If we have some other vector, I'm going to call it u. If that vector u, it's got some number of, well, let me start at the initial point. It's got some amount, doesn't have to be whole number amounts, but just for our convenience, we'll make them whole number amounts. So 3 in the I, so 3 in the I, and then 1, 2 in the J, but those J's are going downward, right? How are we going to depict those going downward as opposed to upward? Well, they're just negative. So -2 J's. And those together are going to make our vector U. So if we wanted to add these together, while we certainly could pick up that vector U and place it head to tail on the vector V, and then draw that kind of resultant vector in between, draw this, and try to count up how many over and up it takes to make that one, we already know how many overs and up it takes. It takes 1, 2, 3, 4, 5, 6, 7, 8 of the I-hats. So you want to take V, oops, yeah, go ahead, I'll make it brown. V plus U. Well, it's going to be that 5i plus that other 3i. It's going to have to go over 5 and then over another 3. So the 5i plus the 3i. What's it going to have to do in the J? Well, it's going to have to go up 1, 2, 3, 4 in the J. So it's going to have to go 4 in the J. And then -2 down 1, 2 in the J from the other vector. So we really can just combine like terms. And that gives us a nice, solid, computationally valid description of that resultant vector just by adding the components. And we don't even need the diagram to do that, though I do like the diagrams, you know that. But if we had a vector that was, say, 7i hat plus 4 j hat, and a vector u that was -3i hat plus 2 j hat, and somebody said, hey, take vector v and add vector u. One of the nice things about this component form notation is if we write out that 7i plus 4j and we want to add the -3i plus 2j, even if you didn't know these are vectors and didn't know what the arrows and hats meant, your mathematical intuition at this point would say that, well, those are like terms and those are like terms. Well, what do we do with like terms? Well, we combine like terms, right? And we'd end up with 4i plus what, 6j? And we get our resultant vector. What if some meanie came up and said, hey, I want you to take vector v and subtract vector u instead? Would we be at a complete loss? Or would our mathematical intuition suggest to us how to handle that? Well, ideally, your mathematical intuition would say, well, could we just distribute that negative and then collect like terms? And absolutely. Turn into what, plus 3i minus 2j? So we'd end up with what, 10i plus 2j? And that would be a resultant vector. What does that look like visually, the subtraction? Well, if we've got our 7i and 4j for our v, our vector u was what, -3, so back that way and up 2. So our vector u is 1, 2, 3, 1, 2. If we took that v plus u, okay, again, we're grabbing that vector u, putting it head to tail, and that result that we built, four I plus 6j, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, should seem reasonable. The subtraction is a little bit, undo more than I wanted there. That subtraction instead visually is a little bit weirder. We got to turn this vector u into the opposite of the vector u. But the nice thing is it's the same direction, just, or same magnitude, just the opposite direction. If that's vector u, that's its opposite. If you combined those two vectors, they'd cancel each other out. So visually, again, what should it look like? It should have a lot of x, a little bit of y, a lot of x, a little bit of y, a lot of x, a little bit of y, with a result, oops. So instead of having to lay all this out perfectly, we can handle it more numerically. Now, all of that presumes that we are either given our vectors in this nice component form, or that we're able to take magnitude direction information and turn it into component form. Now, the best part of the story here is that you guys already know how to do that, whether we know it or not. Let's say we have this vector v with the magnitude of v being, I don't know, let's go with 12. So the length of that vector is 12 at, let's say, 30 degrees to the horizontal. So we're given that that angle to the horizontal there is 30 degrees. Well, that's great, but if I want to add it to or subtract it from another vector, I'd really like to have it in component form. And to have it in component form, I'd have to think of it in a Cartesian coordinate system with x's and y's, and we'd have to be able to figure out, well, how long is that length versus how long is that length? Oh no. If only we had the tools to figure out the sides of a triangle given its hypotenuse in one of the angles. But of course, we have those tools. That's what we've been studying for weeks now. If we want that horizontal component, what function do we associate with that horizontal component? We know that the cosine of that 30 degrees has got to be equal to that horizontal component. I'm going to call it A over the 12. So 12 times the cosine of 30 degrees is that A length. So how far is this vector in the eye? It is 12 cosine 30 degrees in the eye. How far is it in the J? Well, we know that the sine of that 30 degrees is, going to call that B over 12. So that 12 sine 30 degrees is our B. So where is it? 12 sine 30 degrees in the J. And we have a very exactly accurate values for how far up and how far over, what the different components of this vector are. And frankly, we could even turn these, because that 30 degrees is so nice, we could even turn this into 12 times the cosine of 30. We know what that is. It's a square root of 3 over 2 in the I, plus 12 times the sine of 30 is 1/2 in the J. So that's going to be, what, 6 square root of 3 in the I, plus 6 in the J. And we've got an exact value for the components of that vector. If we had another one, let's say a vector u with the magnitude of u being, doesn't matter, how about 8? The magnitudes are always positive because they're giving us a raw size. And let's say it was at, I want to go fun, at 135 degrees from the, I got to be careful with horizontal, because I defined that as kind of the positive horizontal. So from the, I'm going to say positive horizontal, just to be careful there. So if we wanted to put that in component form so we could add these together, well, then I'd want to draw it. It'd be nice if I could draw it in the same diagram, but where am I going to draw it? Well, we could draw it head to tail if we wanted to. But nice thing is, we don't have to. We don't even really have to draw it. It's just kind of helpful to draw it. But remember, where it is doesn't matter. It doesn't have a position. It is going to be at 135 degrees to that horizontal, so it's going to be facing that direction, 135 degrees. And how long is it going to be? Well, it's going to have a length of 8. So that total length is 8. And again, if we want to determine its component form, we would need that length. And because it's headed in the negative direction, we expect that to be a negative number of i's. And its vertical displacement, B, A. So if we want to find those two, again, gosh, if only we had tools for finding vertical and horizontal displacements given lengths and angles. Well, again, that's what all of our tools do. Frankly, we don't even really have to be setting up these equations every time. That horizontal is always going to be the cosine. That magnitude The hypotenuse is always the magnitude, is always going to multiply over. So that vector u is going to be 8 times the cosine of the 135 degrees in the eye. That cosine 135 degrees will automatically become negative, so we don't even have to worry about the negative, plus 8 times the sine of 135 degrees in the eye. We often generalize this, by the way. Our vector u, notice that 8 is the same in both of them. So we could factor it out if we wanted to. Factor out that magnitude of u. Ooh, but we have to talk about multiplication for that. Let's go, okay, we're going to talk about multiplication tomorrow in vectors. And then this cosine and sine, those angles are the same because they're both depicting the angle that we're referencing. So cosine in the I plus sine theta in the J. But oh, this idea of factoring out of a vector, our intuition says we should be able to do that notation-wise if this adding and multiplying means the same thing adding and multiplying always did. But we're going to have to talk a little bit about what it means to take a value, a scalar, call it A, and multiply it by a vector V. So multiplication is going to become a little bit complicated. And we're kind of going to have to save tomorrow for talking about multiplication. But before I give you a short preview of that, questions about this idea of finding vectors in component form and using that component form to add and subtract vectors using our kind of normal algebraic notation that we're used to. You guys fairly happy with that idea? By the way, just for completeness, if we had a vector in component form, say, 3i plus 4j, just to make it fairly simple. Again, that means our vector is 3 units in that direction and 4 units in that direction, which I've drawn poorly, I'm sorry. So it's 3 that way and 4 that way. If we wanted to find the magnitude of that vector v, sorry, that vector w, well, we know the horizontal and vertical length. Again, if only we had a tool for finding that hypotenuse length on a triangle. Do we have such a tool? Are all of you screaming at your screen, Pythagorean theorem? Dominic is anyway. Yeah, we know the square of that component plus the square of that component will equal the square of w. So if we square root that, now technically square rooting it would give us a positive or negative, but magnitude's always positive, so we get to use the positive version. And that Pythagorean theorem builds us technically a formula for the magnitude of any vector. It is the square root of the sum of the squares of the components. It's just Pythagorean theorem. I want to make sure you guys have that before you walk out today. So we'll certainly play with more of this stuff tomorrow. We've got a fair amount of discussing kind of vector logic to talk about tomorrow. But before we do that, before I let you go today, I do want to give you a little bit of preview about some of the issues about multiplication. You may have recognized as you went through your studies that we have multiple ways of writing multiplication. We could write it That way, the parentheses aren't necessary. It's the fact that they're up against each other, right? The parentheses just stop it from looking like 32. This could just as easily be 3a, and the fact that they're up against each other says multiplication. We could also write that as 3 with a little dot. We go, oh, that dot means multiplication. You also, at some point, were writing multiplication with a little cross. It is an X. It is a cross, not an X. So we have the cross notation for multiplication, the dot notation for multiplication, and the juxtaposition notation, the up against each other, to depict multiplication. Hopefully, at some point, you wondered, why are there different notations for multiplication? That's not true for addition, subtraction, even division. Well, division, we have the fraction bar, I suppose. So, this divided by that. We also have that other symbol, division. Wait a minute. Is the division symbol just a depiction of a fraction? Yes, that is why the division symbol looks like that. It's a little tiny picture of a fraction. Is that weird or what? Yeah, maybe not. Anyway, but why are there 3 different kind of standard notations for multiplication? The reason is because those 3 things mean completely different things. If you're talking about vectors. If you're talking about numbers, they might as well be the same. But 3 times a vector like that, it's referred to as scalar multiplication, multiplying a scalar, just a value, by a vector, that's this juxtaposition version. It's very different than taking a vector and dotting it with another vector. The dot product in vectors. Completely different results. V cross U, the cross product, if they're vectors, completely different result, depending on the vectors. They mean very, very different things. In vectors, if you wrote this, somebody would say, no, that's invalid. You cannot dot a scalar with a vector. It doesn't mean anything. If you took one vector and put it up against another vector, they'd say the same thing. That doesn't have any mathematical meaning. When you're talking about vectors, these things mean very, very different things, and we need to talk about that. So multiplication gets a little complicated in vectors. So we'll start that discussion tomorrow. Any questions before I let you guys go? As I said, section 8.3 has a lot of stuff in it. It could really be 3 or 4 sections broken down. So start reading that section, start playing with it. But yeah, we got a lot to talk about. We got to talk about scalar multiplication. We got to talk about dot product. I'll talk to you a little bit about what cross product means. We really save that until physics and calculus because it does require higher dimensional spaces than 2. But I want to kind of show you what it is talking about. And we've got work problems to talk about. We've got all kinds of stuff to talk about in vectors. So still several conversations, but start reading that, start looking it over, start playing with it, and bring good questions because they help our conversations. Okay? Okay. If anything comes up between now and tomorrow, send me a message, let me know. If not, other than that, I'll see you then. You're welcome. Dominic, find some place that's warmer. You look cold.